This is the chapter 1.1 to 1.4 physics quiz from level M. Let's start. It's not a hard quiz, it's really easy. Oops, sorry. Let's start. So which statement about the temperature and the sensation of hotness are true? So a person experiences sensation of hotness when heat flows into their hands. When heat is flowing into somewhere, you're gonna feel the energy go in, so it's gonna be hotter when it's something's flowing into. When something's flowing out of your hands, you're gonna feel colder, so you feel the sensation of coldness when heat flows out of your hands, but hotness when it flows into your hands. So here it says coldness and into, so no, it's wrong. Temperature is the degree of hotness in a body. This is the definition of temperature and it should be memorized, so this one is correct. The sensation of hotness can be used to accurately measure temperature. No. Sensation is a feeling of hotness. Temperature can you be used to accurately measure? Or like, temperature is the degree. It's how hot something is. But the sensation of hotness is a feeling. You can't measure a feeling. The sensation of hotness is a quantity that can be measured. Like I said, sensation and quantity do not go together. It's not something you can measure. So making it wrong. Let's move on. Okay, so for this question, it is saying, in order for the pressure law, a fixed amount of gas is sealed in a rigid cylinder, volume 10, initially at negative 73 degrees Celsius and 800 millimeter of mercury. In order for pressure law to be applicable, so pressure law to be applicable on a fixed amount of gas, which of the following quantities must remain constant? Whenever you see pressure law, no volume must be constant. So pressure, I'll write them all three laws for you at the end of the video. Law equals V constant. So that's for pressure law. Now let's move on to the next part. It's if the pressure of the gas becomes 1200, new temperature to the nearest degree Celsius would be. So they want their new pressure to be 1200, right? And now we have volume, it stays constant, so we don't look at it. And we have this temperature and this pressure, so we know that it's P over T equals P over T, or P1 over T1 equals P2 over T2. So our pressure 1 is 800. Our temperature 1 isn't negative 73. Negative 73 is in Celsius. We want it in Kelvin. So negative 73, you're gonna add it to, you're gonna do this, plus 273, which is gonna be 200, equals 1200, which is the new pressure they want, over T2. We need to find T2. Wait, let me just make sure that negative 73 is 200 plus 273. It's obvious, but sure. Yeah, 200. So now 200 times 1, you cross multiply like this, like you do this by this, then divide by this. Let me do it on my calculator really quick. You're gonna get temperature 2 to equal to 300. Now you're gonna say, oh, there we go, that's our answer. No, this is in Kelvin. We want our answer in Celsius if you be careful. So to make this into Celsius, you subtract 273. So 300 minus 273 would be 27 degrees Celsius. That's your final answer. Let's move on to the next question. See, 27 degrees Celsius. Okay, list thermometric properties. So whenever you see volume of a fixed amount of gas at a constant pressure, it's a thermometric property. But mass at a fixed amount of gas, mass is the fixed amount. So it's not really changing anything. It's not a thermometric property. Hardness of an egg, I'm gonna say this in Arabic, شو دخل أبو. It has nothing to do with thermometric properties. Nothing. It's literally like, if you get this wrong, I actually don't know what to say. So no, definitely not. Length of mercury in a tube, yes, it is, because we know mercury expands with temperature, and it's also, mercury is one of the most important things found in a thermometer أصلا. So you have to have it there. Next question. Okay, so here they're telling us that at 300 Kelvin, the average speed of a hydrogen particle is this. Okay, now your new absolute temperature is 1200 Kelvin. Look, when you have two temperatures both in Kelvin and they quadrupled, which means they times by 4, okay, you just look at the speed and multiply it by 2. That's it. All you do. It's because it has something to do with the velocities of these particles and the kinetic energy with the, or like energy and temperature and constants. Just to make it easier to yourselves, when anything quadruples, this just multiplied by 2. That's it. It's half of how much you increase temperature. Okay, this is the exact same thing. So the amount of gas is kept at temperature T, the average speed with their velocities, the average kinetic energy is E, temperature is quadrupled. If temperature is quadrupled, kinetic energy also quadrupled, because kinetic energy and temperature are proportional. They're proportional. I don't know what it's called. So, and the speeds, they're also proportional, but to half of it. Okay, so whenever you see speed, it's just half of how much the average kinetic energy's value is. So that's it. Okay, this is a thermocouple. So, first question's telling, what does a thermocouple measure? Oh wait, sorry, I'm not underlining. What does a thermocouple measure? Oh my gosh, underline. What does a thermocouple measure? Thermocouple measure temperature. But not any temperature, it's like really specific temperatures. So, yeah. Now, which two wires are made out of the same material? Wire W and wire Y. If you're ever stuck in the exam, they're the two wires with the same thickness or thinness. Wire Z, as you could see, is thicker, but it's usually the ones that are connecting to the galvanometer, whatever it's called. What does meter X measure? Meter X is a galvanometer and it measures the current. Okay, it's like an ammeter but more precise. What statement describes a thermocouple? This question here, we need to memorize it. Thermocouples have a high heat capacity? No, they have a really low heat capacity. See? Thermocouples have a relatively high precision, like I told you. Like ammeters, but really precise. So yes, they can only measure high temperatures. No, they can measure really low and really high temperatures. They have a slow response. No, they have a very fast response to temperature changes. Now let's move on. The absolute temperature of a gas at 150 degrees Celsius is, just do 150 plus 273. And that's gonna give you 423, which is your answer. You're gonna say, why don't we do 273.15? Usually in the exam, when they're gonna ask you, just do 273. Because I see that 273.15, when you do it, it doesn't work or rarely works. Okay. So here they're telling you that you have a fixed amount of gas at a constant temperature of 25 degrees Celsius throughout the exam. Be careful. What's the constant here? You need to underline or be aware of these things. Constant here is temperature. So we know that this is Boyle's law. Boyle's law. Whenever you have Boyle's law, your T is constant. Okay? Pressure law. V is constant. And gas law, I forgot what it's called. Wait, let me remember. Charles law. Wait, Charles law is pressure constant. So keep these in mind always when solving. So this here, we know that temperature is constant, so it's Boyle's law. So the initial pressure is 1 atmosphere and its volume is 12 centimeter cubed. Pressure then increased to 3 atmosphere. Now look, temperature of the gas K to the nearest integer is, we know it's staying constant, but they want it in Kelvin instead of Celsius. Just do 25 plus 273 equals 298, which is your answer. To find the above volume, we need to apply Boyle's law. What does Boyle's law states? Boyle's law states that V1 times P1 equals V2 times P2. So V1 P1 equals V2 P2. So what we're gonna do is we're gonna take the P1, which is 1, times V1, which is 12, equals B2, which we're trying to find, so question mark, times P2, which is 3. So 12 times 1 gives you 12, and this equals to 3 question mark times question mark. So this is just a box, so 3 times 4 will give you 212. So that's how you solve this question. So let's move on. Did I skip one? Yes, I skipped one. Okay, next question. The initial pressure of dilute gas is 8 atmospheres and its volume is 15 centimeters cubed. For Boyle's law, we need the temperature and the mass must remain constant. Mass always must remain constant in all 3 of these rules. So, doesn't count. So now, we need temperature, like I told you, Boyle's law. Now what we do is, again, V1 P1 equals V2 P2. So our initial pressure and volume is 8 times 15 equals 30 times P2. Once you do this, you're gonna get it's equal to P2 equals 4, and that's what you get when you solve it. So that's your answer for this question. Now let's move on. Here we have an example of Charles' law. Let's read. A fixed amount of gas initially at 27 degrees Celsius and has a volume of 8 centimeters cubed. Pressure constant. When we said pressure is, or well, P constant equals Charles law. So to find the final volume, you need to apply Charles' law because we said pressure is constant. By the way, guys, Charles, it has to be apostrophe after the S. Spell it wrong, you get the whole mark gone. Has to have the apostrophe after the S. Be careful. Now, Charles' law says that it's V1 over T1 equals V2 over T2. So V1 would be 8 centimeters in this case. T1 would be 27 plus 273 because we know that it's in Kelvin. It has to be in Kelvin. So let me do it really quickly. 27 plus 273 is 300. So that's your T1. So 300 equals V2 is what we're trying to find. T2, they told you temperature is halved. Absolute temperature is halved. So you don't go halve this thing. You don't halve 27. You take 300 and you half it. Half of 300 is 150. So now you do 150 times 8, then you're gonna divide it by 300, which again you're gonna get 4. So V2 equals 4. That's how you solve. By the way, in the exam, if this comes written, please write down all your formulas. Write down everything. Now moving on. Did I skip something? No. Okay, for Charles' law to be applicable, pressure and mass must be constant. I already said this a lot. If the volume of this gas is increased... Okay, wait, so we know the rule already. It's V1 over T1 equals V2 over T2. So if our volume increased, so what's our initial volume? It's 12 over T1, which we just calculated, is 27 plus 273, is gonna be 300, equals V2 is 18. T2 would be, let's calculate, 300 times 18 would give us 5,400. When we divide that by 12, we get 450. So here it's 450 Kelvin. We want it in Celsius. So 450 Kelvin minus 273 is gonna give us 177 degrees Celsius. So that's how you solve this question. Now let's move on. Okay. A fixed amount of gas is heated in a sealed rigid cylinder of volume 20 centimeters cubed. Initially, the gas is at negative 23 Celsius and 600 millimeter mercury, heated to 27 degrees Celsius. We need to now apply the pressure law, because if you want to find the final pressure, we need to do pressure's law. Why? Because your volume is gonna be constant. A fixed amount is fixed mass, okay. And in a rigid cylinder of this, they did not change it. The only thing here they changed so far is the temperature. So we know temperature cannot be constant. Temperature here is definitely not constant, so it's definitely not Boyle's law. And since they want us to find the final pressure, we know that we have to find pressure, so we need to use pressure's law. So now we know that where volume is useless and we only need the pressure and the temperatures. So to find the final pressure of the gas to the nearest integer is, so we know it's P1 over T1 equals P2 over T2. P1 would be pressure 1, which is 600. Let me do it this side. 600 over T1, negative 23 Celsius. Again, negative 23 must be converted to Kelvin. So you're gonna add it to 273, which is gonna give us 250 degrees Kelvin, equals pressure 2, which we're trying to find, over 27, which we found a million times to be 300. So now let's calculate. 300 times 600 equals 18 and 4 zeros. Divide by 250, we get P2 to be 720 millimeters of mercury. And that's how you solve this question. Let's move on now. A fixed amount of gas of volume 20 centimeters cubed, initially at 7 degrees Celsius and 2.5 atmospheres. The temperature is raised, so it can't be, we don't care. Temperature of the gas is raised to 147 and pressure is doubled. Since temperature was raised, pressure was doubled, volume has nothing, no change to it, so we ignore it. Oh wait, no, we don't ignore it. This is the ideal gas law. They want us to find the volume. So, okay, so this is ideal gas law. This is the law that is, contains everything. This law states that V1 times P1 over T1 T1 equals V2 P2 over T2. We need to include everything in here. So now let's see, we have our V1 is 20, P1 is 2.5 over T1, 7 plus 273, which is 280, equals our new volume times 5, which is our new, because they said pressure is doubled, so 2.5 doubled is 5, okay? That's where I got the 5 from, over 147 degrees Celsius, which is 420 Kelvin. Once you solve all of this, you're gonna cross multiply first. So 420, multiply it by 20 times 2.5, you're gonna get 21,000, divided by 280, you're gonna get 75. So question mark times 5 equals 75, leaving question mark to equal 15. And that's how you solve this question. That's it. It's really easy. Once you know the formulas, only apply them and guarantee the 100. So here we just need to label things. Whenever you see a thermometer and it's stuck in a container that looks like this, that has steam in it, this is the steam point. Steam is obvious. This is boiling water, and here there's another one that says something going up. This would be heat, because you need to heat the water to evaporate or boil it. So that's for this question. Memorize it. Okay, what are the hazards of calibrating a mercury thermometer? We know mercury is a very toxic material. So it's toxic mercury, so we need to be careful. That's one. It's very hot when you're doing it because you have a steam point and you have to steam it and whatever. And fragile glassware, because you're using glass. If you knock something down, you're probably gonna get hurt. Cold, no, it has nothing to do with cold. Toxic steam, I think it's only if you inhale it, or it has something to do with if you drop it to the floor and inhale it. But when calibrating it, not an option. Just toxic mercury, extreme heat, and fragile glassware. Now, in this question. So here what we do is let's read the questions first. In order to plot a point 10 centimeters and 0 degrees Celsius on this graph on the thermometer, the thermometer is placed in contact with melting ice. Whenever you see 0 degrees Celsius and placed in contact, it's always melting ice. And whenever it's 100 degrees Celsius, steam of boiling water. These, memorize them. Now here, the length of the mercury in the thermometer, 22 centimeters. So what you do here is, we go to the graph and we need to look where is 22 centimeters. So we know, if you look, that between each 10, there's 5 spaces, 5 spaces, making each one 2. So if this is 20, then this is 22. You're just gonna take your eyes or your pen or whatever, and you're gonna drag it. And when you move it all the way here, you're gonna find out this is 60 degrees Celsius. Let's see. It's 60 degrees. The size of 1 degree Celsius on the thermometer in millimeters is... What this means is just asking us how to calibrate the thermometer. So they want it in millimeters. So what we have to do here is we go to the top, the highest point, which is 100, and you find its distance, and you go to the lowest point, which here is 10 centimeters away. You need to find the 0 and the 100, not the highest and lowest. Sorry, I worded it wrong. You find 0 and the 100, and you see what their length is. So here it's 30 and here it's 10. So you do 30 minus 10 divide by 100. You're gonna get 20 divided by 100, which is 0.2 centimeters. Okay, they asked for it in millimeters, meaning multiply by 10, which is 2 millimeters. That's it, how you find the size of 1 degree Celsius on the thermometer. Let's move on. Okay, here they want us to label the graph. So, like we said, of course 100 isn't gonna be lower than 0, so 0 and 100 have to be the temperatures, and here it just makes sense that 10 is before 50. That's it. Not like you have to memorize or anything. When the thermometer is immersed into a liquid of temperature 50, the height of the mercury column is... so you need to find temperature 50 and the height. So what we do is you need to find the 100 and the 0, and we need to count how many spaces is between them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this means that each one here is 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So they asked us when it is 50. Here's our 50. We go and we connect it down. Now we need to find what this is. So if here's your 10 and here's your 50, you need to count how many spaces between them. 1, 2, 3, 4, 5, 6, 7, 8. 50 minus 10 is 40. 40 divided by 8 means that each one here is 5. So this is 15, this is 20, 25, 30. So that's how you find your answer. You could continue 35, 45, 40, 45, 50. But we needed this one here, and when you go down, you find that this one is 30. That's how you find this answer. Now, here, this is asking us how do we calibrate a thermometer on the Celsius scale. You need to put our ice point always to 0, and our steam point is always 100. Both are defined for atmospheric pressure. So we know our atmospheric pressure is equal to 1 times 10 power 5, which is 1, 2, 3, 4, 5 zeros, right? So they want it in kilopascals. This is in pascals, okay? So kilopascals, we take away 3 zeros, bye-bye, and we're left with 100 kilopascals. And that's it. Now, let's move on. Last question. The name of the lower fixed point is, which is here, this is the ice point. Ice point always going to be at 0, and it's always going to be in melting ice. The upper, which is here, which is the 100, is always our steam point. It's always at 100 degrees Celsius, and it's always in boiling water. Memorize it. You can't solve it otherwise. Memorize them. And that's it for our 1.1 to 1.4 quiz. Hope you understood everything. Have a good day. Bye.